So yeah, I'm going to talk about the data reduction pipeline for the Keck Planet Finder instrument. And I'm going to start off, well, I was actually kind of hoping that there would be other talks about data reduction pipelines that would go through this nasty flow chart that I have here and explain what these pipelines actually do. But since there haven't been, I'm going to have to walk through a little bit of it, I think. So unfortunately, it doesn't look like I have a pointer here. Can't see my mouse, can you? Yeah, here we go. Oh, I'm not sharing the slides. That's why the mouse wasn't showing up. Is that working? Yeah. Okay. Okay, so if you were paying attention closely to Andrew's talk, you'll notice that there's a lot of different components of the KPF instrument. So we have data from the exposure meter here, which is essentially a low resolution spectrograph that reads out very quickly. We have data from of course, the two science cameras here, and we have a bunch of data from the fiber injection unit that has information about the telescope and guider camera images and such. Those all go into what we call a level 0 data product. This is just the raw data, essentially, as it's read from all these different things. That data is passed into some basic image processing routines there, where you do bias, flat, dark correction, typical things of CCD processing. We also make nightly stacks of calibration data, so laser frequency comb data, thorium argon. We make nightly wavelength solutions there. Those all feed into creating a level 2 data product where we actually go and extract the spectra from each one of those traces that you saw. And again, if you paid close attention to Andrew's talk, you'll notice that there's 5 traces across each order on the KPF instrument. 3 of those are from the science target, one's from the sky, and one's from the calibration fiber. So we extract all of those and turn that into a one-dimensional spectrum for each of the orders. We then incorporate the exposure meter data and figure out exactly when the photons hit the CCD as a function of wavelength so that we can properly account for the motion of the observatory towards or away from that star over the course of that exposure. We also do sky correction, where we measure the sky in the sky fiber and subtract that from the data. And then once we have this one-dimensional spectrum, we combine that with a cross-correlation mask, where we've defined the lines in the spectra that we want to actually calculate the radial velocity from, calculate those cross-correlation functions, and then use fitting to find the peaks of those Gaussian-looking CCFs. We also will calculate some canonical activity indices from various activity indicators in the spectra. We're not going to do any sort of correction on the actual data, but we're going to include those activity indices with the final data products. Oh, and then one other little instrument I forgot is this whole separate calcium H and K spectrometer that goes through much of the same process as the rest of the data to produce the final data products. Okay, so that's the basics of what our data reduction pipeline does, and most of the data reduction pipelines for most of these instruments operate in a much similar way. Now, KPF instrument, or the data reduction pipeline, I think is fairly unique in that we thought a lot about the architecture, the design of the software, and we didn't try to reinvent the wheel on a lot of the algorithms and how we actually solve for the radial velocities. We built on heritage from other EPRV instruments to grab those algorithms to calculate the CCFs and such. But we focused a lot of our effort on designing the software. We actually treated this data reduction pipeline as a critical component of the instrument itself, without which there is no working instrument. We employed software industry best practices in design. We hired professional software engineers to write much of the code. We have a robust testing infrastructure, version control, coding standards, review process, and all of this, as you would find in a professional software project. And we always plan for this to be open source and available to the community in a way that the community can actually submit contributions and not have to worry about breaking the code, and it'll be easy enough for people to maintain and actually incorporate those changes in. So some of those best practices are, first of all, we operate everything under Docker containers. So Docker containers are like little Linux virtual machines that run within your machine. And this allows for complete portability. That means you can run this pipeline on a Windows machine, on Linux, on Mac. It's always running under exactly the same operating system with exactly the same software installed in that operating system. So you can always be confident that the results will be the same no matter where the data is processed. We have a formalized Git flow development process, which is just a fancy way of using GitHub and reviewing pull requests and such. We have automatic documentation using Sphinx. This is the typical Python package documentations that you've probably seen before, and I'll flash up a screen of that later. We're employing continuous integration and testing using Jenkins. So continuous integration is whenever we submit a change to the code, a suite of tests is automatically run on a remote server. Now, this was actually a particular challenge for our pipeline because radial velocity pipelines often need huge amounts of data to actually do any tests. And the public services that do continuous integration are not designed for that, this large amount of data. So we had to set up our own continuous integration server on a local machine so that we could do this. And the software is fully parallelized at the recipe level, which I'll mention. Now, we designed and built the software within this Keck data reduction framework. So this is similar to like Dragons at Gemini. It's a ecosystem under which Keck prefers that all of the pipelines are going to operate under. The framework itself is sort of the outermost layer here in green. It does things like keep track of an event queue, handles parallelization, and then underneath that, we have a pipeline level, which is written by us. Pipeline keeps track of the order of operations and the higher level operations like logging. Under that are the primitives that actually do work. These are the functions that actually do something. One of the nice things about operating under this framework is that a lot of the things that we didn't have to do things like think about logging or configuration. All of that is actually handled by the framework and multi-threading as well. But we decided to utilize the Keck data reduction framework in a novel way that wasn't necessarily designed for, but we decided we need it for maximum flexibility. So we designed this system of recipes. Recipes are essentially an order of operations for the pipeline to go and execute all the steps that you want to do. This is an example of a recipe here on the right, and you'll notice it looks much like Python code, and it essentially is, but it's very limited Python code. We essentially rewrote a lot of the parser, the Python parser interpreter, so that we could incorporate this recipe system. The reason why we didn't just have straight Python recipes is because that's a serious security risk. This Keck framework is designed to run on remote servers, and we can't have just random Python code being sent up there to execute on a server. So we took the Python language and broke it down to just the very basics of what we needed. And this allows us to do all sorts of clever things within those order of operations, have loops and if statements and conditionals, and whatever we want, essentially. The testing framework is quite robust. We have 3 levels of testing. Regression testing is what I was talking about with continuous integration, and that just makes sure the code is functional whenever we make a change to the code. We didn't introduce a bug that breaks everything. We also have a performance testing level to make sure that when we make changes, we didn't all of a sudden make the code slower by a factor of 100 or something. And we have verification testing to make sure that the scientific output, the rate of velocities in the end, are either improving with new changes to the code or not getting worse at least. This documentation, like I said, is automatically built by Sphinx. We incorporate doc strings into the Python functions, which are, essentially say what the inputs and output of that function are. And we send it through this Sphinx machinery that builds all these nice websites for you. And this is, commonly what you would see if you're developing in any Python package. So let me talk a little bit about the products that are produced in detail. So I kind of went through it on the flow chart. The level 0 product is just a collection of all the raw data products from the various subsystems. Then we have level 1 data, which is the extracted and wavelength calibrated 1D spectra. We also have the low resolution one-dimensional spectra from the exposure meter. We have the calcium H and K spectra. And then in the level 2 data, we have just the RVs, cross-correlation functions, tables of the RVs. In the data reduction pipeline, we've also implemented these Python data model objects that make it much more convenient to interact with these data products. Essentially, these are multi-extension FITS files that may have dozens of extensions. And instead of having to go read documentation and see, is the 12th extension the RV table, the Python data model objects help you do that. So you can actually use the pipeline to read and write. And then one of the most interesting, I think, is the quick look products, which I think a lot of Python or a lot of packages, data reduction pipelines have this. It's essentially a collection of plots that allow us to do quality control, check the data, see what it's doing, and in real time. And when I say real time, I mean that from readout of the 2 CCDs to radial velocities and the collection of quick look plots, it's about 8 minutes. So that includes transferring from the mountain down. We're actually processing at Caltech right now. In the future, that'll be on the mountain. And so we get a look immediately at the data products within a few minutes of data collection, which of course is extremely useful as you're trying to conduct observations during the night. So the current status of the pipeline is that we're sort of in a shared risk mode as the instrument is in shared risk mode for the next semester. Our data products are produced and somewhat documented, but they're not necessarily finalized or optimized yet. We're still kind of iterating on operational techniques, so how we utilize various calibration data and even the order of operations. We don't have great quality control checks in there yet, and that's simply because we don't understand all the failure modes of the instrument quite yet, because it's new. And our documentation is still in progress. So with all that being said, the code will be released open source in a matter of weeks. It'll be transitioned over to ownership by Keck Observatory with ongoing support and development from the KPF team. But yeah, so in a matter of weeks, you'll be able to go download the code, look at all of it, read it, use it, and try it out yourself. So thank you. I'll take questions.
Okay, thank you very much, BJ. Got time for one question while our next speaker comes up to the front of the room. Francesco, I saw your hand first, and Ben's gonna bring you a microphone.
Yes, so it's related to this open source, but also the verification moment. I mean, our experience is that let's formulate the question. How do you verify actually the quality, especially in terms of radial velocity? Is it full automatic?
No, it's human. Like we have automatic tests that are running on a nightly basis, producing those results. And we're not going to like reject a change to the pipeline automatically based on, an RMS increase or something. But we have that data to track for a human to look at and make those decisions.
Okay, that's reassuring. I mean, and the second question related to that, isn't there a little bit of a tension between making open source a code that you actually have? I mean, you have to be an expert in understanding the instrument. Otherwise, I mean, it's difficult. You are looking for every photoelectrons to treat it correctly.
I think that's true to some extent. There are definitely components of the pipeline that you don't have to be an expert in the instrument. We just heard talk about barycentric correction details, and that kind of thing could be contributed by someone else and entered in the pipeline, and they don't have to know the details about the instrument.
Okay, let's thank BJ again. If you have additional questions, please